Welcome everybody to the second lecture in the model engineering class, where we will continue our journey along the foundational aspects of this course. Today we will particularly focus on model-driven software engineering and its core concepts and how these concepts relate to one another. So model-driven software engineering at a glance is defined by considering models as first-class citizens in the software engineering lifecycle. So models are not kind of a side effect, but they drive in some of these subdisciplines, and if they are not driving it, then the software engineering process is at least dedicatedly using these models or different kinds of models throughout the process. So the way in which models are defined and managed is based on the actual needs that they will address, and therefore there are different subdisciplines. MDSE as a general domain defines sound engineering approaches to the definition of models, model transformations, development processes of these models and the transformations, and model management. So let's look at some of those aspects and the concepts that are subsumed by this term. Primarily, we will engage in abstraction from specific realization technologies. If you recall from last week, we already talked a lot about abstraction, and abstraction is also at the core of MDSE. So we abstract from particular software technologies that are used to realize a certain software system and try to solve or to describe the problem and to define a solution to that problem on a higher abstraction level. This higher abstraction level then naturally enables us to enable such nice features like interoperability between different technological solution spaces, right? So it enables portability. We only need to create one model to describe a problem or a solution to a specific problem, and then we can use transformation approaches, we will come to that later, to translate or transform our given abstract solution to a technology-specific solution on a specific technology that we chose to solve a certain problem, right? Another aspect or concept that is at the heart of MDSE is automated code generation. So the models don't only serve the purpose of communication and specification, but the models also are the primary artifact. So they are used to generate at least parts of, in some examples, even the full code of the software solution. And this, of course, also increases a lot the productivity and the efficiency, because modeling only needs to happen once, and then we can generate code on different technology spaces, for example, automatically. And the last aspect and the last concept that MDSE emphasizes is the separation of concerns by means of the separation of development between infrastructure and application code. We will come to that later in the process of this course. So the MDSE methodology ingredients are then concepts, the components that build up the methodology, the notations by means of the way to represent those concepts, processes and rules, the activities that lead to the production of the final product, and of course tools by means of applications that ease the execution of these activities and that coordinate these activities. So the MDSE equation, to sum up, is models plus transformations equals software. And we will look in both of those aspects. So we will look into the modeling part and also into the transformation part today on a more generic or abstract level to introduce these notions. And in the subsequent courses, we will then look into the concrete aspects of how to create models, how to create transformations, and how to apply that. So let's look at the MD jungle of acronyms. You might have encountered already that in the literature there are many different abbreviations that are kind of directed toward the domain of model-driven engineering or model engineering, and today we will try to build, to structure these different acronyms. So model-driven development is a development paradigm that uses models as the primary artifact of the development process. So the models are the primary artifact and they drive the entire software development lifecycle, right? So at every stage of the lifecycle, different kinds of models drive the development process in a whole. as a whole. Model-driven architecture is then a particular vision of MDD that was proposed by the object management group. So while MDD is a more generic notion that doesn't entail any specific kind of models or modeling languages that you should use, but it describes the generic sense of model-driven development, model-driven architecture is then a particular flavor or vision of that is realized using models only defined by the object management group. Okay, so you use OMG-defined models to drive the development. It's a particular vision. Still follows MDD. On a broader sense, model-driven engineering is a superset of MDD, so it entails more aspects compared to MDD because it goes beyond the pure software development and encounters or entails different or all of the artifacts that belong to software engineering. Yeah? For example, deployment specification files and so on. On the largest scale, we then have model-based engineering or model-based development, MBE, which is a softer version of the MDE, where models do not drive the process. So means models are used heavily throughout the process, but they don't drive. They are not the primary artifact. So here is where we also use models as a specification means or as a communication means, as an agreement between different software engineers or software engineer and tester, for example, or the DevOps department and the deployment and the software engineers. So the core means of a conceptual model serving the purpose of communication and specification. So this is trying to structure a little bit the acronyms and the jungle of acronyms that we encounter in the literature. Let's try to get a better understanding of why MDSE is so powerful from our perspective. And this slide emphasizes this. So when you use So one could ask, why do we engage in MDE? Why don't we just build software right from scratch and solve the problem? And this slide tries to emphasize our core understanding, which is any technology-specific solution like Java or XML can only work on the solution space. So we are very high on a technological specificity, while we are having a hard time to translate the problem that origins in the problem space, in our domain, toward the solution space, which is then Java as a programming language, right? And with MDE or MDSE, we try to define the problem using a domain model. So we use the terminology of the problem domain to specify what is our problem, and then we translate this or transform this into the solution space by using model transformation approaches, or the other way around. This is shown by the dashed lines also, reverse engineering. So we can also create models in reverse from existing legacy code that we might have. So the overall idea is that we are much better aligned to the problem domain, where domain experts can also be engaged in the definition of the problem, and then we can subsequently go into the solution space, where we are technologically seen much more richer, but we are much more abstract, so much farther away from the problem space. So this is the overall a motivation of MDSE, kind of. As already noted, models are one of the central aspects, one half of the equation, so models plus transformation. So we need to first get a better understanding of what is a model, and for this we want to understand what are modeling languages. In the literature, there is a dichotomy of modeling languages proposed. So we differentiate domain-specific modeling languages from general-purpose modeling languages. Domain-specific languages are characterized by being very close to a very specific problem domain, and therefore they are very powerful when being applied in that particular domain, while they lack some generalizability, so we cannot easily use them in a different domain. Examples for that are HTML or SQL that only work, SQL for example, in the domain of relational databases and to query and to define the data properties, right? We cannot easily use this in a different context. General purpose modeling languages, in contrast, try to be domain agnostic, so independent of a particular domain, and enable application for different purposes and in different domains. An example here is UML or Petrinet that you can use to specify software systems for university software, for healthcare, or for whatever domain you can imagine. So they don't have a notion of a domain specific concepts as part of the modeling language itself. Yeah. All of those languages, so domain-specific, alike general purpose modeling languages, are then defined by means of a meta-model. So meta-model is a very, very core concept throughout this course. And meta-models are defined in what we call a meta-modeling stack or a meta-modeling hierarchy. Yeah? So a meta-model is, as the name implies, a model on a higher abstraction level, on a meta level. Yeah? So with a meta model, we define the concepts and the relationships that can then be used on the lower level in this meta hierarchy. So the example on the right hand side, we see on the M1 level a model which is representing a video that has a string as a title, and this is an instance of aspects or concepts that are defined in the meta model on the M2 level. So on the meta model level, we define that we have attributes and classes, and these two concepts are instantiated on the M1 level. So video is an instance of class, and the attribute title is an instance of the attribute. Going one level higher, the concepts that we use on the M2 level are themselves instances of the concepts that are proposed on the next higher level, on the M3 level, on the meta model. On the meta model, we say we have an abstract concept of a class, which can be an instance of another class. So a class can be inherited to other classes. And then we see that both attribute and class are kind of instances of this class notion. We will come to that in the next lecture in more detail, but this is the generic notion of these hierarchies of languages and how we design the modeling languages, right? So when we design a modeling language, we design a meta model on the M2 level, and therefore we always use a well-specified language to specify our meta model, which is in the modeling world always the meta model. The second aspect of the equation are model transformations. So model transformations are used to transform models. They can transform models from one modeling language into models adhering to a different modeling language, so model-to-model transformations, or they can transform a model adhering to a specific modeling language into, for example, source code, yeah, or a textual representation. So there we call these kind of transformations model to text, yeah, and the text can then be source code or specification or deployment files or whatever you can imagine, a documentation. Yeah? So those transformations are very powerful in order to automate the driving that models should do in the model-driven engineering process. And the specification of those transformations can be manifold. They can be defined by model mappings. So assuming we have two different modeling languages and we want to create a transformation, we can define mapping tables where we say this class or this concept of the source modeling language is transformed into this concept of the target modeling language, and then we need to define the mappings between the attributes and properties to make sure how this semantically behaves. Yeah? So we can define model mappings or model weavings or correspondency rules. And throughout this class, we will also go into some of the frameworks and some of the technologies that are provided in the EMF world to realize such model transformations. So more on this throughout the course. So to bring all of those concepts together, this seems to be a very hectic slide, but I will try to explain to you how to read it. So let's start from the right-hand side and top to down. So we have meta-modeling language, one meta-modeling language. If you recall back from this slide, the meta-modeling language is on the M3 level. So we have one meta-modeling language. And from this you see the dashed arrows. They say is defined using. So we said a modeling language is defined by using a well-defined, predefined meta-modeling language. So we can define several, this is why you see two blue boxes, several modeling languages that all are defined by using the same meta-modeling language. If we go one step left, or one step to the left, we can, for each modeling language that we have defined, we can think about many different models that have been created by modelers by using or defined by using a well-defined modeling language. Yeah? And to instantiate this in a concrete example, and to also be kind of something that we will discuss in the next slide, the meta-modeling language could be the meta-object facility of the OMG. The modeling languages could then be the UML class diagrams or the use case diagrams, and the models are then concrete class diagrams, concrete use case diagrams of a specific software system. Yeah? If we go to the second row, we can also see that not only modeling languages can be defined by using a meta-modeling language, but also transformation languages are defined using a meta-modeling language. And then we can follow the same abstraction as for the modeling layer. We can define transformation definitions using this transformation language, and those transformation definitions can then be applied on the model to generate or to realize software artifacts, which could be source code or models adhering to a different modeling language, yeah? Which can then be used on a dedicated modeling platform. Yeah? So this is the overall setup of model-driven software engineering, and we will go throughout this course, we will go through this entire figure. We will talk about the meta-modeling languages, we will talk about modeling languages, transformation definitions, and how to execute them and how to bring them together. When we talk about model transformations, as I mentioned, they are also using some meta model. So like indicated on this slide on the right-hand side, a transformation language is itself defined by using a meta modeling language. And this has a very powerful side effect. So because you see here now, we have the meta object facility in the center on top as the meta model, right? From this meta model, or from this meta modeling language, we define our model transformation language. Yeah, so you see the model transformation language conforms to the MOF, and then we can say any source model source meta model A on the left hand side and the source meta model B on the right hand side, they are both also conforming to the meta object facility. Okay, so the model transformation, that's the way from transformation language to meta modeling language, and the modeling language to meta modeling language left to right is what we see here flipped upside down. Yeah. And because all of those, so meta model A and meta model B, as well as the model transformation language, conform to the same meta modeling language, we can immediately define this mapping between MMA and MMB. So we define the model transformation using a mapping-based approach on the meta model level. And then we execute this model transformation execution on the concrete models. Yeah? So this is very powerful. We define a mapping and rules on the meta model level, and then we can apply them and execute them on any model that you can imagine that is an instance of these meta models. So this is very powerful. This is how we facilitate the strength of abstraction, and we bring this strength or we situate it in the modeling world or in the model-driven engineering world. So models in MDSE and conceptual models generally can be classified based on different criteria. So for example, based on the concrete syntax, we can differentiate textual, graphical, or hybrid ones. So textual ones is using a textual, maybe a domain-specific language to create some models. Graphical is something that you should know from all of the UML courses that you might have be part of. And hybrid is a combination. So there are no limitations, right? The purpose for which they are created, like to specify requirements as a design blueprint or as a deployment specification, and also, of course, also content-wise, but also purpose-wise. Predictive models means models that we use to predict this futuristic behavior. Prescriptive, to prescribe, so to design a future software system that we want to build. So before we start developing code in Java, we create models to prescribe how the system should behave and how it should look like. Or descriptive, the other way around, we already have a software system and we create models to represent and to describe an existing system, to describe it on a higher abstraction level for means of communication and understanding. Yeah? So generally, when we talk about how to use models in MDSE, a kind of a distinction is very useful that we also see, of course, in the UML hierarchy of languages. We differentiate static models that describe how a system is built, the data that a system is using or transforming, the structural shape and the architecture of systems. And we differentiate the static models and the static view from the dynamic models that emphasize the dynamic behavior of a system by showing the execution possibilities. And this is, of course, what you also see in the UML family of languages, where you have well-defined differentiation between the static view on a software systems, for example, by means of a class diagram, from the dynamic view, which is, for example, a use case diagram or an activity diagram that shows the behavior of the system. So the powerful means of bringing this together is using these models in the software development process, where we said we differentiate the development of the application software and the infrastructure. So application development only involves modeling. We can generate much of this code. And in the infrastructure development, we can use the models also to specify certain aspects on a higher level of abstraction, and then use some transformations to generate the software code. Yeah? So the idea here is that we strongly simplify the application development, and we foster or support at least also the infrastructure development, which is much more complicated and uses also a lot of deployment and platform-specific aspects. For this, of course, we need new development tools to realize this vision of MDSE. So we need tools that support the language definition, in our case, modeling language and transformation language definitions. So these are called meta-modeling platforms. We need editors that support the creation of models and engines to execute the model transformations. And of course, this all should be customizable. So we would like to have editors for modeling, for repositories, for simulation, verification, validation, all of that stuff. Because if we say that models drive the software engineering process, then we need, of course, development tools that support all of the core aspects of software engineering, like development, debugging, testing, deployment, also, or execution and simulation, also based on the models. So you can replace software by models. So we need model creation, model testing, model deployment, model execution, simulation, all of that aspects also in this software environment. There are then different approaches how we can do that. Also historically, if you think about computer-aided software engineering, that were the forefathers of our meta-modeling and model-driven engineering platforms today. And our focus, as already stressed in the MD jungle, is the model-driven architecture, the OMG-specific flavor of model-driven engineering. And we will now in the following go briefly over the core features of MDA to introduce you to some industrially standardized notion of MDE. So the model-driven architecture primarily emphasizes on the interoperability through the platform-independent model. So generally, MDA differentiates three kinds of models: the computation-independent model, the platform-independent model, and the platform-specific model. And by, again, describing the problem in the domain it adheres to, we are able then to in a stepwise manner, translate this problem specification into a technology-independent solution, and then in a final step in a technology-specific solution. And this enables us, of course, interoperability, separation of concerns, and it enables primarily also reuse, because we can reuse the same model on the problem domain level, also on the platform-independent level, and then just create new transformators that transform this model into, for example, source code in one specific platform or in one specific technology. So let's look at this in action. So model-driven architecture, like I mentioned, we start off with in the modeling space where we have a technology-independent model, for example, a UML class diagram. We create this model, then we use some automated transformation process to translate this into an intermediate level model that is still platform independent, and then in the final step we can transform this into part of the source code that realizes this system. I mentioned already there are three different kinds of models involved. The computation-independent model, where we specify requirements and needs at a very high abstraction level. This can then be subsequently transformed and refined in a platform-independent model, where we define the behavior of the systems in terms of stored data and performed algorithms without any technical or technological details. And in a final step, we go toward the platform-specific models, where we, as the name already indicates, we define all the technological aspects in detail that are required or used to solve kind of our problem. Yeah? Let's go through this step by step with one example. So a computation-independent model, CIM, could be defined by this process model here. We see a process model that has some start event and an end event, and in between some activities like new customer arrives to a counter, check customer identity, and so on and so forth. So this is a computation independent. It doesn't give us any insights of how to automate this, how to realize this, but it provides us a view on the behavior of the system and what it kind of supports. A platform-independent model can then be created from this by looking at the data and the structures that are necessary to support such a system. So in this respect, we could still think of business entities like an account that has some constraints on it, that has some properties like the number, which is an integer, the balance, which is a floating number. So here we could use UML, for example, or any other language to define on a still technology agnostic, so independent from the concrete technological solution or implementation. We can define the problem on a much narrower, much lower abstraction level. And this model then, of course, can be translated into a platform-specific model. So here's the example where we use enterprise Java Beans as one concrete technology solution to solve or to realize the system that we would like to have. And then we just use some stereotyping from this specific domain. In our case, we use UML profiles. So we just then can relate to enterprise Java Beans, stateless, stateful beans, and we can really specify this on this very specific level for the technology that we are using. And you can then think that we can use the same platform-independent model here and we can translate this into an arbitrary number of platform-specific models. Yeah? So there is one platform-independent, whereas there can be many platform-specific. For each platform that we are interested in, there can be a platform-specific model, like one model using enterprise Java beans, the other model using C++ or C# or any technology that you would like to use. So what we need, of course, as already stressed, is to have powerful tooling that supports us in the creation of such profiles. If we stick to the UML domain or to the OMG domain, then we would define profiles. Profiles are a means to extend existing UML languages to introduce domain-specific semantics. Yeah? So in this case before, we instantiate this by saying we have a stereotype of an EJB base and an EJB bean, and we can use this then, of course, to extend UML class diagram for this particular specific technology-specific domain of EJB. Advantages of such an approach are standardizations of the meta levels using the OMG meta hierarchies that we introduced today, and of course the separation of the platform-independent model from the platform-specific model, which should emphasize reuse, as I just now explained to you, with the one-to-many relationships between one platform-independent model and potentially many platform-specific models. Disadvantages are, of course, that there's no specific support for the development of the execution platform in the modeling languages. So the modeling language practically is limited to UML with the profiling, where we can only define extensions. So we cannot kind of filter out aspects that we don't want. And therefore, we also have to some extent limited code generation, where we don't have typically method bodies or user interfaces integrated into that aspect. Whenever we want to do that, we can also follow a model-driven engineering approach, where we use very specific modeling languages that are all defined by ourselves and not following the OMG standard way. Yeah? And then we have the full power to define whatever language we need that might also incorporate method bodies and user interface, because then, of course, we would be very, very domain specific, but this is, of course, possible in domains where we execute these models very often. So, for example, in the automotive domain, there's a plethora of very rich domain-specific languages that they use, and transformation languages to transform these models created on different abstraction levels. One platform to support the engineering of languages and also of model transformation is the Eclipse modeling framework, which is what we will use throughout this course heavily. So more on this follows in the future presentations. One aspect that I also want to emphasize as a closing remark is the differentiation between modeling tools and drawing tools, because in many obstacles when we talk about modeling, people also misunderstand that, for example, PowerPoint or Visio are modeling tools. They are not modeling tools, they are drawing tools. They can be used to create nice visual drawings, nice visual graphics of certain aspects. And of course, if you think about the process model that we have seen earlier, you could create such a nice model, such a nice diagram also with PowerPoint. The problem is, and the differentiation, is that PowerPoint has no clue about the meta model that underlies the process model that has been created. So it doesn't know the underlying meta model, and with the meta model it doesn't know about the rules of which elements are allowed to be connected with one another. Yeah? So a modeling tool, in contrast, knows about the semantics, so it can also highlight to you where are errors and where are things not correct. Yeah? You can find here an analogy. From the left-hand side, you could say an integrated development environment like Eclipse or VS Code, and a text editor. You can create Java files in both of them, while only the IDE is capable of validating your Java file, giving you hints for syntax errors and even suggestions for autocomplete. A text editor cannot do that, because a text editor only stores the text and enables you to write text. Okay, so this is the differentiation. So drawing tools are very powerful in creating early sketches, but drawing tools are stupid in the sense that they don't know about the semantics of the modeling language. So they cannot make sure that the models are valid, and they cannot even, of course, execute the models. Yeah. Likewise, IDE and text editors. In an IDE, you can execute your Java program on your Java files. In a text editor, you cannot do that, right? So this is a very important distinction that you should be aware of early on in this course, because it's at the heart of what we are doing. And once you talk about using models for driving engineering projects, of course you need to execute these models. Of course you want to make sure that you are only creating models of good quality, and all of this then requires modeling editors or modeling tools. This is also reflected kind of in a discussion in the history when you talk with software developers and their perception of modeling. In the early stages, there were notions like diagrams are, after all, just pretty pictures, or quotes like, no user is going to thank you for pretty pictures. What a user wants is software that executes. Yeah, and as I already mentioned, with powerful modeling editors, we can provide that. So diagrams are or models are not just notation. Instead, models have a well-defined syntax by means of the meta model, right? And you can then validate models based on this meta model in modeling tools. And also, of course, as already stressed, we can use the model transformations and the code generations to actually generate code and execute our models. So the models are driving the engineering process and are not just an additional effort, a throwaway product throughout the process of realizing a certain software product. That was the message of today, so I hope you now have a decent understanding of the jungle of MDSE and how the different concepts are composed. In the next week, we will talk about concrete examples of meta modeling, and we will go one step further along the way toward becoming model engineers. Thank you very much.